All right, everybody. This is a video on geometric sequences. Let's get started. Geometric sequences are sequences of the form some ratio r to the n power. Okay, so when we're looking at the ratio r to the nth power, we could consider three possible cases. When absolute value of r is 1, when absolute value of r is less than 1, or when the absolute value of r is greater than 1. Okay, so let's first consider the case where the absolute value of r is 1. Well, when is the absolute value of a number equal to 1? When that number is 1 or that number is -1. So if r is 1, what kind of sequence will we have? Well, 1 to the first power is 1, 1 to the second power is 1, 1 to the third power is still 1. So the sequence that we will get is just 1, 1, 1, 1, 1, which converges to, of course, 1. Okay. Now, when r is a negative number, what do we know about negative number? Well, -1 to the first power stays -1, but -1 to the second power is going to be positive. And then -1 to the third power going to go back to -1, right? So, and then -1 to the fourth power is going to be +1. So this sequence is going to bounce in between +1, -1, +1, -1. And of course, we cannot say that it's going to converge to a number. So we say it diverges. All right, so that is the case where absolute value of r is 1. Now, to me, I like to visualize this on a number line. So I'm just going to go ahead and draw the number line and see what the three cases are, right? So case number 1 is when absolute value of r is 1, meaning when r is at 1 or -1. And as we have seen, when r is 1, the sequence converges to 1 because that's all it is, just 1, 1, 1, 1. And then if r is -1, then the sequence diverges because it bounces back and forth between 1 and -1. Okay, now in between here is when r, absolute value of r, is less than 1, right? And the exterior here and there are when our absolute value of r is greater than 1. So let's next consider the middle, when the absolute value of r is less than 1. Well, what number is less than 1? Well, I think I'm going to pick, say, less than 1 could be like here is 0, right? So less than absolute value is less than 1. So it could be like a positive number or a negative number where the value is less than 1. So let's look first on the left here, where that is a negative number, say negative. Oh no, I switched my left and my right, darn it. So actually that one is on the right, okay? So where the R is positive right here, right? So 0.75 to the n power, well, it's gonna get smaller and smaller and smaller until it is approaching 0. So we would say that the sequence will converge to 0 when r is a number, a positive number less than 1. Okay, now consider the case when r is a negative number less than 1. Well, as we have seen before, even exponent is a positive number. Odd exponent is a negative number. So it bounces from negative to positive and then negative to positive. But because we are multiplying by 0.75, we only have 75% of what we had before. So guess what happened? Even though it's bouncing back and forth between negative and positive, it is getting smaller and smaller as well. So this sequence is going to also converge to 0. So we would say in between -1 and 1, meaning when the absolute value of r is less than 1, we will have a convergent sequence. Okay, now let's go then to look at the third case, meaning when absolute value of r is greater than 1, greater than 1. Okay, so we're looking at what, say 1.15. Okay, so I get my left and my right correct this time. Okay, so here negative number, right? Negative number with value greater than 1. And so negative as a ratio r raised to the nth power, again, it's going to bounce back and forth between negative and positive, but because you're multiplying by a factor that is greater than 1, it's in this case 1.15, meaning you will have 115% of what you had before. So the value get larger and larger and larger as you go, right? So so then this is definitely not only that it is oscillating and it is getting larger and larger and larger. So that sequence diverges. On the right-hand side, you have, in this case, we're not bouncing in between positive and negative. We just nicely get larger and larger and larger because we are having a factor of 1.15 or 115% of what we had the term before. So yeah, it's gonna get bigger and bigger and bigger, and it will get infinitely big. So when r is greater than 1, the sequence also diverges. Okay, so here is a summary of what we just did. If the absolute value of r is less than 1, the sequence converges to 0. And if r is 1, then it converges to 1. Otherwise, there is no limit as n goes to infinity. And that is how geometric sequences work. Okay, so let's use that. And our job when we are using this geometric sequence theorem is that we need to recognize that geometric sequence. Okay, so consider an to be a sequence looking like this. Okay, so we would have to recognize, is that a ratio r to an n power, right? Actually, there are two of them. So the first one here, the ratio is 0.06. The constant, okay, remember limit law applies, can be pulled out to the front. And this we know when the ratio is less than 1, that thing converges to 0. So 5 times 0 is still 0. This one is this with the ratio of 1/3, and that converges to 0. So overall, we would say 0 minus 0 is 0. So the sequence an will have a limit of 0, or it converges to 0. Okay, now next we have a sequence looking like that. Well, when you have a just one term on the denominator, right? We can split those and think of them as e to the n power, and the other one, well, you see e to the n power is going to just be 1, right? So the limit as n goes to infinity, well, 1 is going to stay 1 no matter where n goes, right? And the other one is going to be pi over e. right? So our ratio there is pi over e. Pi is roughly 3.14 and e is 2.7. So you know that this number is larger than 1, right? And when r is larger than 1, we are here. We are here. And when we are here, we diverge. So overall, this sequence will diverge. And that is it for now. Okay, up next, we are going to talk about BMS and recursive sequences.